Okay, guys. So let's begin. For the past 2 days, we've been talking about removable discontinuities, algebraic ways to get rid of the discontinuity if it's removable. Factoring was our first one. Rationalizing and complex fractions was the second strategy. Give me a twitch, bro. Give me a nervous twitch. All right. So, but not all discontinuities can be removed. For instance, if I gave you guys this, this discontinuity at 3 can be removed, right? Because it just equals 1. These cancel, right? But what if we had this? It's supposed to be a 3. You can't cancel that out. There's nothing you can do to get rid of that. When you have a non-removable discontinuity, your answer is either infinity, negative infinity, or undefined, because the limit doesn't exist. If it existed, then you would have been able to remove it. Okay? So today we're going to talk about what to do when you come across non-removable discontinuity. The second thing we're going to talk about is limits at infinity with rational expressions. So a rational expression is when you have a polynomial like 6x minus 3 over x squared plus 2. And you want to find the limit of this at infinity. This is a rational expression at infinity. The answer to this one, I hope you guys will be able to answer this as quick as I can by the end of the day. The answer is 0. Okay? So we're going to get you to know how to do that. We're going to do more infinite limits and limits at infinity when we get to 3.11 and 3.12. Today we're mainly focusing on rational expressions, but on these days we're going to do the same thing but with trig functions and exponential and logarithmic functions. So limits at infinity, and I treat them all different because they're all a little bit different in the way that you have to deal with them. The concept's the same though, infinite limits and limits at infinity. Tomorrow I'm going to give you guys a little piece of gold called L'Hopital's rule. L'Hopital's rule is a real treasure because basically it will find you the limit of any removable discontinuity function with one simple trick. It's awesome. So all those strategies I showed you past 3 days, kind of don't really need them anymore. L'Hopital fixes it like in 2 seconds and it's way easier. So it's nice to know those strategies because honestly, L'Hopital, the ones with the square roots, L'Hopital might actually make that a little more complicated. So the rationalizing one's good. Complex fraction one's kind of good. But that whole factoring thing, never again. You don't have to do that. L'Hopital takes care of it. But technically, L'Hopital does work on everything. So that's tomorrow. We've talked about this quite a few times, infinite limits. As x approaches c, this is infinity because it's coming at infinity from both sides, right? The limit of f of x as x approaches c here is negative infinity because it's going down to negative infinity on both sides. And whenever it's approaching positive infinity on one side and negative infinity on the other, it doesn't exist. Those are infinite limits. Okay? So let's take a look at this one here. Example 1, I've printed it for you. Now, first of all, basically what I want to do is I want to find what is the limit of this function as x approaches 3. In other words, I want to know what is the limit as x approaches 3 of 1 over x minus 3. Can I do direct substitution? No. Can I remove the discontinuity? No. This is a non-removable discontinuity. I can't factor and cancel anything out. I can't rationalize. I can't do complex fraction stuff. So that means my answer is one of 3 things. Positive infinity, negative infinity, or it doesn't exist. It's one of the 2. It's a vertical asymptote. And so it's doing something. So let's go ahead and see what it is. The way we're going to deal with this is we're going to revisit the table. Now, whenever you're trying to find the limit of a non-removable discontinuity like this, you need to look at it from the left and right separately so you can know, is it positive infinity, negative infinity, or neither, right? So we have to look at both sides of the limit. So what x value am I trying to approach here? I'm trying to approach 3. Now we already know that it's undefined at 3, right? Now what we're going to do is we're going to plug in a number really close to 3. So what number is really close to 3 on the right over here?
2.99.
That's over here. I'll take that. 2.99. You take 1,000th off. What about on the right?
3.001.
Good. And so what we're going to do is we're just going to plug it in. Okay. So we can just plug those numbers in because that doesn't make it undefined. So let's do that. I'll show my work. Whether you want to show your work or not is up to you. I think it might be helpful. Otherwise, you might wonder where these numbers came from later. But I'm just going to plug in 2.999 minus 3. And what that's going to give me is 1 over negative 0.001. Somebody with a calculator want to help me out with that? Thanks. Okay. Let's do the same thing with 3.001. So what I'm doing is I'm plugging in, I can't plug in 3, but I'm plugging something really close to it to see what this function doing as I get closer and closer to 3. All right, so let's try 3.001. 1 over 3.001 minus 3. That's going to be the same thing, but the positive version of it. So now this requires some interpretation here, okay? We already know that this is a non-removable discontinuity. So if I were to graph this, what would I expect to see at x equals 3? A vertical asymptote. Now, as I'm approaching 3 from the left, what are my y values doing? They're shooting down really, really fast. That's what that means. And what about on the right? Shooting up. So what's the limit from the left? What am I going to say? How about from the right? And total answer? That's good. That's it. So when it's a non-removable discontinuity, the answer is either going to be positive infinity, negative infinity, or does not exist. And the only way to do it is with a table, really. Just plug numbers in that are really close to the number you want and see what's happening. Okay? So, let me throw in at you guys. 2 things I want you guys to pay attention to on this, though, before you begin. First of all, man, there's a bug in here. All right, so we're squaring it. What happens when you square a negative? So pay attention to that. Second of all, this dude here, don't ignore him. He's just chilling there. But don't ignore him because it affects the answer, right? So I want you guys to go ahead and see if you can find the limit of this function as x approaches 1. It's non-removable. Can't factor that out or cancel or anything. So you're either going to be infinity, negative infinity, or does not exist. The way to do that is you do the left and the right with a table. Go for it. Give it a few seconds. It is. The final answer is negative infinity. And the reason for that is because both of these are negative infinity. Now let's see why they are what they are. So first of all, Aaron's not with us, so I can't ask Aaron. But I will ask Max. Max, what number am I approaching here?
You're approaching 1.
My x value I'm approaching is 1. This is a non-removable discontinuity, so we have to do the table to get the answer. Jennifer's not with us, but Isaac's not with us. But Jacob's with us. Jacob, what can I plug in to the left? Since I can't plug in 1, I'll plug in a number really close to 1. But what would I plug in from the left? You would plug in 0.99. Nakaya, what would you plug in to the right?
I think he's talking to you. You don't know the answer.
No, we
I
didn't.
know the answer.
Why don't you just take it
1.001.
out of there?
Yep, stop playing.
Thank you, Maya Bailey. All right.
Why is my government out there, Jay?
because this is a government institution. This is public school. This is funded with government money. I've got to. This is a government institution. Let's just tell them the truth, Maya.
No,
It's complicated, Manny. But her mother is my sister's cousin husband. I don't know. All right. So, Roxanne, what is the y value at 0.999? Negative 1 million is correct. Manny, what is 1.0? What's my... Actually, I think it's still negative. You know why? Because here's what's going on. Now, I told Juliana could tell her a way to do this without a calculator, because you guys can't. So check it out. First of all, 1 over, don't forget your negative in the front. Let's say I wanted to plug in 0.001, right? Minus 1. Well, we already know what that is. That's 0.001, right? Un momento, por favor. Here's what we do. No calculator needed. Ready? 1, 2, 3. Makes the bottom 1, right? 1, 2, 3. Makes the top 1,000. So don't really need a calculator. It's negative 1,000. Oh, but I forgot to square it, didn't I? So let's redo that. Let's redo that. Shush. Shush your berry, sir. All right. So we can still do this without a calculator. Ready? So what's 1 times 1?
1.
How many numbers are behind the decimal?
3.
So I'm going to do 1, 2, 3, 4, 5, 6 because you're squaring it, right? 0.001 times 0.001. You just have to have that many numbers in front of it afterwards. And then that means I'm going to move it over 6 times, so the top becomes 6 zeros when you move your decimal over. That's too many zeros. But there it is, negative 1 million. So now Ryan explained this very clearly. It's basically the same thing as last time. It's going to be infinity, but since you're squaring it, the bottom's going to be positive always, right? But this is going to make everything negative. So you end up with negatives in both spots. So we still have a vertical asymptote, but whether we're coming from the left or the right, they're both negative infinity, and therefore the final answer is negative infinity. So that's objective number 1 for today. How do you find the limit of a function at a non-removable discontinuity? And the answer is what? Chart, table, right? There you go. That's the answer. So how do you find the limit of a function with a non-removable discontinuity? The answer is table it. All right. Now we're moving on to objective 2. Yes? Yeah. A bit. I actually don't.
Mr. Bailey, I'm hungry.
I'm sorry to hear that you're hungry.
Mr. Bailey, you're supposed to help me.
I might. But would you like to pass the nurse for a Band-Aid?
No, because she went to sign in, and that's not good.
Just sign with your blood. There's only one person with a sense of humor as me. That's good, Ashley. You're the only one that laughed at that. All right. So let me ask you guys. 1 over 1 and 1 over 2. Which one's bigger? All right. What about 1 over 3? Which one's bigger?
1 over 2.
What's happening to this fraction every time I make the bottom bigger? So every time you make the bottom bigger, the fraction gets smaller. So how small would this be? Really small. How small would that be? There's a number for that.
Pretty small.
It's called infinitely small.
Let's look at decimals. It might help you if we look at decimals. Let's look at some decimals first, okay? So what's this equal? 1.
0.3.
How about 1/10? How about 1/100? How about 1/1,000,000?
0.0000000.
Can you tell me what this would be then?
0.
The answer is 0. So when you let the bottom become infinitely large, the fraction approaches 0. All right? When you let the denominator become infinitely large, the fraction approaches a value of 0. So, go ahead and write down this slide here, please. You can write down the picture. That's fine. Go ahead. So guys, here's what I want you guys to walk away from here. And can you guys put a minus under that too? Because it doesn't matter whether it's positive infinity or negative infinity. Here's the fact. When you have 1, and matter of fact, let's not put 1, let's put C, because it doesn't matter what the top is. The point is, if this bottom is growing infinitely large, you're plugging in infinity here, so no matter what the power is, that bottom is growing infinitely large, then that fraction basically just goes to nothing, right? The bigger the denominator is, the closer it gets to 0. So if you let it go to infinity, it's approaching 0. And that's, Manny was actually asking a relevant question. He's like, well, can you get to infinity? Does that, or did we just say you're close? Well, the point is you can't say you're at infinity necessarily. You can say what it's approaching, right? As I approach infinity, the fraction approaches 0. Okay? So we're not actually there, we're approaching it. You can't get to infinity, it's infinity, right? So anyway, but now here's the graphical representation of this, and we've already done this in this unit. As x goes to infinity, that means I'm moving to the right. And as I move to the right, what y value am I approaching? 0. So whether it's left or right, the point is it's bottoming out at that asymptote there. That's a useful fact that we're going to use today. Let's go ahead and write down this problem here. So guys, what I'm about ready to do is I'm going to show you something that I'll just call the division trick. Okay? It's a name I made up, so don't go using that with your future calculus teachers because they won't know what you're talking about. But I call it the division trick. They'll know the strategy, I just don't know if there's a name for it or not. So I call it the division trick. Now here's the thing, I'm going to show you the division trick and then we're never going to use it again because right after I show you, you're going to see there's a shortcut for it. But the thing is, the shortcut doesn't make sense unless you do the division trick. So I want you to understand it first, but after that we're going to use a shortcut, right? So the division trick, by the way, this only works for rational expressions at infinity. Okay? So let's write that. Works for rational functions at infinity. Works for rational functions at infinity. So you can't apply this in other circumstances necessarily. Okay? Okay, here we go. Here is the division trick. Ready? You're going to divide every term by the term in the denominator that has the biggest power. So what term in the denominator has the biggest power? X squared. So I'm going to divide everything by x squared. Now, whenever you do something at the top and the bottom of fraction equivalently, does that change the fraction? No. It just changes the way it looks. So it's a total legal math move. Why would I want to do that? You'll see at the end. But for now, just follow my lead. So I'm going to divide everything by the biggest power in the bottom. So I'm going to put x over x squared, right, plus 1 over x squared. On the bottom, I'm going to have what here? X, yeah, we'll get to that. But yeah, for now, x squared over x squared. And then what's last? 5 over x squared, right? Just take everything and divide it by the term in the bottom that has the biggest power. Okay, now, I can say that these two limits are equal because these two functions are equal. Because I just used a rule of fractions that allows me to rewrite the fraction in a funny way. Once again, why did we do that? You'll see it at the end. But we're going to use another rule about fractions. Don't you guys agree that when you reduce a fraction, it's still the same? So I'm going to reduce all these now. And therefore, I can still say that these limits are equal, right? Because I'm not changing the function really. I'm just changing the way it looks. So what's x over x squared reduced to? No, 1 over x. This one does not reduce, so I'm going to leave it the same. How about this one? 1. X squared over x squared is 1. And the last one doesn't reduce either. So why did we do this weird little trick, making this thing look so ugly? Well, you'll see why. You guys remember on the last slide how I told you that the limit of 1 over x to any power, or c, any number, over x to any power as x approaches infinity is what? 0. So I could just do direct substitution here. Watch. What's this going to equal when I plug it in? That one's going to be 0. How about here? 0. 1 over x to any power as x goes to infinity will be 0, because as the bottom gets infinitely large, the fraction goes to 0. How about here? 0. All of those things that are 1 over x or something over x to a power go to 0. That's why I did that. But there's one that's left. This guy. What's the limit of 1 in infinity? It's 1. Why is it 1? Well, let's think of it as a function. Here's the function 1, right? If I go out to infinity, what's the y value? It's 1. Okay? So it's just 1. And what's 0 plus 0 over 1 plus 0? 0 over 1, which is? There's your limit. Remember that example I gave you guys today where I said I hope it gets to a point where I could just put a problem and just go, oh, the answer is 0? You should be able to do that now because we don't need to do this division trick. Let me share with you a shortcut. You ready? Anytime the bottom power is greater than the top power, the answer is always going to be 0. Because when you do the division trick, everything cancels out. Okay? So we have a shortcut now. So if I were to give you guys something like this, the limit as x approaches what? Infinity of, let's be weird, anytime the bottom is bigger than the top power, it goes to 0. Why? Because the bottom power is bigger, and since the bottom power is bigger, which part of this fraction is growing faster? The bottom is going to be growing a lot faster than the top, because the 6th power is bigger than the 5th power. So since the bottom is exploding, what happens to your fraction when the bottom gets too big? It disappears. So your fraction just goes to 0. So there's your shortcut. So we don't need the division trick anymore until we get to the next problem. Ready? We do need to do the division trick again, but I'll give you a shortcut for that one as well. Ready? All right. How about this one here? Go ahead and copy this one down. Now you guys are seeing why why you're writing. I'll talk. You guys will see why the shortcut doesn't apply here, right? They're equal. The bottom power is not bigger than the top. They're growing at the same rate. So now what the heck do we do? Well, I'll show you. The division trick will show us the answer. And then when we're all done, I'll show you once again, there's another nice little shortcut. What are you laughing at? Your hands are up in the air an awful lot. Trying to keep the blood out of there. Flowing around here. All right, you guys ready? Let's do our division trick. This one I'm going to let you guys do a lot of the work. All right, so step 1. David, what am I dividing by?
X squared.
Because that's the biggest term in the bottom. That's the term in the bottom that has the biggest power. Now, could I divide by 2x squared? Yes, but it doesn't. It'll actually just kind of make it uglier and harder to work out. Just do x squared, okay? So go ahead and divide everything by x squared and simplify it. I'm going to ask you what you got. Not the final answer, just what happens if you divide by x squared and simplify each fraction, okay? Go for it. So here we go. This limit that we have on the board already is equal to the following limit. Go ahead, Ricardo. What do we get after we divide everything by x squared?
3 plus 1 over x plus 1 over x squared.
Okay, good. And on the bottom?
Divided by 2 plus 5 over x squared.
Okay, he's right. This is what you would get if you divided everything by x squared. So now, I want you guys to do the next step. I want you to do the direct substitution. Plug in your infinity to each term with an x. And you guys know what happens when you plug in infinity to 1 over x to a power? Okay, so go ahead and do that and see if you get the final answer. Sure. Austin, what's our final answer? It's 3 over 2. Because when you plug in the infinity, this goes to 0, this goes to 0, this goes to 0, and all you're left with is 3 over 2. Now, what's the shortcut for this one? So we know that when the bottom power is bigger than the top, is 0, right? But what about when they're equal? What's the shortcut? There it is. Okay? So you just take the numbers in the front of the two first terms and make a fraction out of them. Okay? So let's review a little bit here. Ready? Yellow's not good. You don't need to write this. You can just watch. Okay, I'm not going to write it again. Let's watch. So, Marcos, what's this answer? 0. Why? You got it. And Jade, I'm going to make a change here. I'm going to change this to 5 now. Now what's the answer? Good. 1 over 1 is 1. Okay? No need for the division trick. Okay, now the next one is a little bit confusing. So this one's not quite as easy. There's still a shortcut. I'll share it with you, but it's a little bit trickier. Okay. So go ahead and write down this one. Division trick together here. Ready? So now, what am I going to divide by this time? X squared. Always the biggest power in the bottom. Now, I've just been lazy. They're all squares. They're not always squares in the bottom, you guys. I'm just, the problems I picked kept doing that. So we're dividing by x squared. So let's do that. Limit x approaches negative infinity. And this is, if I divide this by x squared on the top, what will I have? How about here? Oh, yes, thank you. 2. How about here? Okay, now here's where things get a little bit interesting. Here's where things get a little bit different. Which piece goes to 0 when I do my direct substitution? This one goes away, right? That rule does not apply to this. This is not a number over x squared. So let me show you what we're going to do instead. Ready? This is going to be negative 3. And I'm plugging in what now? I'm going to plug in negative infinity. Now, I don't know if this is technically good math to write, but this is how we're going to do it. I just wouldn't do it on an FRQ. Okay? So, but it makes total sense. So we're just going to do it. But I don't know if I would suggest writing plugging in infinity into a function, because it's not a number. You can't plug in a concept into a function. Infinity is a concept. It's not a number.
Can we like move that x squared down and then put like x to the negative 2? Does that make sense?
You could, but I just don't think it will help. I don't think it will help us get to where we want to be. On the bottom, we have 2 plus 0, right? Okay, now, here's where we get to use some common sense, okay? It may not be common sense yet, but it will be after we practice a little bit. First of all, I can't plug in infinity. It's a concept, right? But let's think about what it means. It means we're plugging in bigger and bigger numbers that are negative. But no matter how big a number is, when you square it, what happens to it? It's going to be positive. Now, here's some more common sense. What happens if you take infinity and you square it or multiply infinity by infinity? What do you get? You get infinity. So it becomes positive because of the square, right? And when you square infinity, you just get infinity, right? Now, what's negative 3 times infinity? It's negative infinity, right? The negative makes it go back to negatives, and multiplying infinity by anything just makes more infinity, right? Now, what happens if you divide infinity in half? It's just infinity.
Well, wouldn't it be positive?
No, because you're dividing by a positive 2.
Yeah,
So
but it's already negative. The function's already negative.
that's where that negative is this one.
Oh.
It's been there all along. So my answer is what? Negative infinity. So that's how you're going to handle that. Now, what's the shortcut? So we don't have to do the division trick. What's the shortcut going to be?
Always the same.
If it's a negative, it's gonna be.
Oh, that's a good guess, but no. Here's why. It depends on three. It depends on three things. What are you plugging in? What are your powers? And what's here? So there's three things you got to look at. So let me give you guys some steps. Ready? Shortcut. I would write this if I were you. Here's a short. It's really not that much shorter, but it helps. Okay. So your shortcut is take the first term on the top and put it over the first term on the bottom. Just the first terms. Because I don't know if you guys have noticed, but in every problem we've done, every other term other than the first one always just cancels out, right? They just always go away, so they're negligible. We can ignore them. All that matters is the first term on the top and the first term on the bottom. So let's just look at those. Then the next thing you're going to do is you're going to reduce it. So, for instance, my first term on the top is 3x to the fourth, right? First term on the bottom is this. Then we reduce it. What does that reduce to?
3x squared over.
The only thing that's not here now is the plus 0. But that's because we knew it was going to be negligible anyway, right? So that's, we had that already. And then what you do is you plug in either positive infinity or negative infinity. And that's what we did. So, and from there, just use your knowledge about negatives and infinity to kind of reason your way to the answers. Yeah.
You said don't write that?
I said do right, because that's how I'm going to say do it from now on.
What you said, like, don't plug in anything.
Oh, like on an FRQ?
Yeah.
Yeah, I don't think you should write this. Like, what I would do is I would write it on the side just to work it out if you need to, unless you can do it mentally. And then when you're done, scribble it out and just put the answer, because that's all they want to see. Yeah, I don't think this would be good math to write, okay? Just so you know. But it makes total sense, so I like to write it. All right. So let's go ahead and do number 1. Now, number 1, I'm going to give you just a split second to do it, because it should be pretty quick. What do you think, Brandon? -2 is correct. Brandon, notice that this power and this power are the same, and when that happens, it's this number over this number. So I have -2 as my final answer. Let's go ahead and jump down to number 3 here. I'm going to give you a split second. It shouldn't take that long. What do you think, Juliana? No. Lisa? 0. You know we're doing number 3, right?
Oh, yeah, sorry.
Okay. All right. So, well, listen, notice the bottom power is greater than the top power. The top doesn't even have a power. And when that happens, the answer is 0. Now we're going to do number 2, and this one I won't give you a split second. I'll give you a couple split seconds because it's going to take a little bit longer. This is the one we just talked about, where the top is bigger than the bottom. So go ahead and work it out. I'll give you a few seconds. What we're going to do is we're going to put the first term of the top over the first term of the bottom. What do we do next, Alyssa?
Simplify.
Good. So that'll be this. Angelisa, what do we do next? Plug in negative infinity. And when you square negative infinity, what do you get, Ashley? And when you divide infinity in half, what do you get, Andy? Huh? Well, we have positive infinity because we squared it. So what do you get when you have positive infinity divided in half? Yep. The answer is infinity. Okay? So, there you guys go. So we learned how to find limits of functions with non-removable discontinuities For that, you use a table. We also learned how to find limits of rational functions at infinity, and for that, you use the shortcuts that I shared with you today. Okay? Time to go.